Hello, and welcome back to Learning with Lee. In the previous episode, we began our discussion of functions. And in this episode, we are going to continue that look at functions by taking a look at a couple of the more complicated things you can do with functions. The first one, and I briefly gave it to you as a bit of an assignment to do between these episodes, was to implement this has-value function, so as that you could get a feel for passing in an array to a function. And the thing is that for the most part, it's identical to if I were doing an integer or a value. The difference is that whereas those are passed in by value, an array is passed in by reference. In case you remember the previous episode, I discussed how, in case I wanted to change this value here within the square root function itself, I would put this little ampersand here. And that ampersand would mean that I would basically be accessing the same spot in memory that if I say passed into it just value 1, then I would effectively be able to modify that same spot in memory. So, in this case here, I've got this. This is what my current one outputs because all I did for it was initialize the array using basically the square of whatever the index for a certain element is. So at element 1, it has 1. At element 2, it has 4, and so on and so forth. So, for example, at element 10, it has 100. So this comparison here of seeing if it has 100, it works out correctly. Then, in case though I were to change this, because right now it doesn't have 1,000 in here, and I were to go, okay, after one time of running, I want this to end up putting 1,000 into that array. So I could go array sub 0, and have that then equal 1,000, and that will actually modify my values up here, even though I'm not actually specifying this by reference. And that's because I'm not going to get into fully yet how arrays happen to be implemented, because that's a discussion for a decent ways down the road, but for now that's probably good enough. And what we can do then is we can do this, and you can see that in here, we don't have it on our first time through this loop, but then we add 1,000 at the 0th location, come back through has value, and now we have 1,000. So that's just a minor thing to be aware of with regards to how arrays and how they're treated differently from your integers, your characters, etc. One other oddity that exists with arrays in functions is that we do not know in a function that receives an array what the size of that array is. So we have to ask the consumer, whoever's calling this method, to let us know how large this array should be. So in the event that somebody gives an incorrect size, such as if I go, say, size plus 50 here, just to really go with something pretty obviously screwed up, this is going to lead to some problems. And that you can see down here, where it's outputting all these other ones down here, and it's actually checking them. And in case we go with wrong enough values, it can cause some serious issues. So this is something that you always also have to be aware of and be careful with, is that you do not want to go, if I did say negative size, or in this case here, well, negative size would be a bit less of an issue because down in here, a negative size would end up just causing us to say, okay, we're greater than size, so we don't even do this. So that's not a real issue. A bigger issue would be in case I tried to do something such as in here, -5. Now that would cause a serious issue. Because while it might appear to work, the fact of the matter is that that right there is still overriding some spot in memory, and I don't know what is stored in that spot of memory. Because whatever it is, it's basically 5 int-sized chunks of memory prior to the first element in values. So that's a really dangerous thing, and it's something that hackers will end up exploiting, and we'll get into some of the stuff that they end up doing a decent ways down the line. But for now, that just is something to be cautious of, be careful with, and understand that at least until we get into more advanced objects, similar to strings that we've already seen a little bit of, that it ends up being something that you have to tell the function how large something is like this. The other topic I wanted to cover in today's episode is what's known as recursion. And recursion simply is the idea that any function has the ability to call itself. So has value could call has value, square root could call square root, Any of these could call any of each other's. However, the major thing about recursion is that it's the ability to call oneself. So if I were to, say, toss bool to string within bool to string and pass in b, then I just would get an infinite loop because this one would get called from the first location, this would call this, basically spawning off another instance of this function, which would in turn wind you up here, jump down into here, and spawn off another one, and eventually you'd run out of memory and you'd be in an infinite loop and you would end up having your program crashing. But what you have to consider it more similarly to is consider it more similar to a for loop or a while loop, in that in the end you're going to need some termination condition. And one of the key things with any termination condition is that we need to make certain that that is the first thing we check for. Because in the event that we're in an invalid state to begin with, we do not want to keep processing in that way. So, all that we have to do here is as we go, let's just do has value for simplicity so as that we don't have to deal with some of the complexities of square root, for example. And for this one here, all that we're going to do is we go, well, first we actually need to make a change so as we can store what position we're at from one iteration of this to the next. So I'm just going to store int pause is int position and put it up here with a default value of 0. So as we start at the beginning of the array. Then what we do is we go, if our position is greater than our size, or equal to actually, then we just want to return false. But if it's not greater than or equal to our size, what we're going to want to return is this expression here, checking if our current element is equal to the value, or what we then want to do is we want to say is that is the next element equal to the value? So in this case here, we just would pass in r, same size, same value, and then we would go one position further. And then beyond that, we can just remove all of this because none of that really is necessary. And that happens to be our recursive version of this. So if I build it, run it, then you can see here, get the correct results of having 100, not having 1,000. And the reason why this works is that, and this is a bit of a tricky thing based upon how I ended up setting up this recursion, because normally what's going to happen is it's going to execute the final one first in this. So if I just had something such as this where it does return has value, or if I did return has value and then put this section over on this side, this would execute whatever the final element in has value is. So it would end up returning false, it would go down, it would hit one where it returns false, then it would evaluate the next one up. However, the way that I had it is a bit of what's known as a short circuit of Boolean logic, and that's that if the current position is true, then this OR expression is guaranteed to be true. So it doesn't matter what's on this side of that expression. As such, we never have to evaluate has value again. We can just stop as soon as this expression here is true. Because then this is going to return true to its parent, which is basically this section here, and presumably whatever was on this side was false. Then it's going to OR them together, get true because this one was true. Doesn't matter that this one wasn't. And it's just going to do that all the way back up through that chain of has values until it reaches the original one. And then it will return the result of this entire expression here back up to somewhere such as up here. For a slightly more complicated version, let's take a look at what it would take to modify our square root function in order to actually be recursive. So, the first thing that we want to do is we're going to need to basically be able to store our guess, because we need to know how decently we're doing on that regard. Then we're also going to need to store the search delta. So both of these now are getting stored up here. So there's that guy, and well, we'll just go with this for search delta. and then we no longer need either of these here. Then what we're going to do, and I just move effectively this up to here, because now this is going to effectively be our loop rather than a while loop. So then what we need to do is we go, okay, what's our termination condition? And our termination condition is the same thing as it was here, in which if this is less than or equal to our threshold, we need to return our guess. And if it's not, what we then need to do is go, okay, we need to shrink our search delta, same thing as before. Then we need to take this once again, same exact thing as here. So we can just basically get rid of these two braces, move this over. We have to also, while we're at it, update up here, this, and this brings up another problem. You note how this one here happens to be what's known as an optional parameter because of the fact that we gave it a default. Right now, because this one here has required parameters after it, this can actually give you errors. So basically what you have to then do is take threshold, cut it out, and put it at the end, because any of your default parameters have to go at the end of your list of arguments. So we need to do that change there, and we need to do that change down here as well. So that'll allow that to actually work and run, but now we need to modify how we call into it if we were to use it. So let's just go with changing these to doubles again, which means that we're no longer going to be able to use this down here. But we don't really care about any of that anymore, so there's that. Then let's just output the square root of 100, so cout square root and value 1, and the line, so as we move on to a new line, and do that for each of those. Then what we're going to have is, this right now is giving us some errors because of the fact that this has an incorrect definition right now, in terms of I don't have the correct arguments in there. So the next thing I need to do is I just go with value 1 and value 1. Alternatively, I could clean this up some, get rid of this. Oh, say I have this square root function, in which what I would do then is I just would go, okay, we're going to copy this guy, move this here, redefine it so it's the exact same as how our original square root function was. And then we have this one down here, and this is what's known as overloading. And overloading means that basically it's the same name that you're using, but the functions are different because of the fact that they take in different arguments. So, in this case here, I need to have a second square root definition. And this is a common thing in which you could also rename one of these to a helper function, because basically what the helper function is designed to do is it's designed to help set up your recursive function. So if in this case here I do something such as return our square root, and within here I'm going to want value, 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 and then the threshold. Oh, and I need to get rid of that also. And then this one right here, I could even make this a mandatory threshold that gets applied, since this one here has an optional one, and this one should only be called by this one. So what this does is this allows us to basically go, I just wanted to do it in the cleanest possible way for how I'm calling it here, and I don't care about how it's actually implemented. I don't care whether it's a for loop, a while loop, some mathematical operation, whether it's recursive, etc. All that matters to me is that I'm getting out the square root of this value. So then down here, there's one additional thing that I forgot to do, and that's that down here, this right now is not actually a recursive function. Right now, this is just going to return guess no matter which code path we go down, just will return either the initial guess or plus or minus the search delta of it. So what we need to do is modify this one here, so that it then returns square root, and we end up going recursive. So what we want to do is we want to go value, we want to toss in our guess, we then want to leave the threshold alone at the end, and before that we want to toss in the search delta, and there we go for that. So that happens to be a reasonably good way for doing this. I could actually make this slightly more compact, frankly. And the way in which I would end up doing that is that what I would do is I would go, okay, down here, I can take this and we're going to use the ternary operator again. So we're going to do that. So if we're less than it, we're going to return our guess. And if we're not, we're going to shrink the search delta by 2. So we no longer need that entire section there. Clean that up some. However, because of the fact that we end up doing this at the end here, we actually need to make a minor change to begin with, and that's that right here. We want this to be divided by 2.0, so as we get the correct search delta for what corresponds to this guess. And if I then build this and I run it, you'll see that we get out the accurate things, and I can uncomment this just so we can go down the entire list of what these do once again, and you can see that we end up getting closer and closer and closer, and getting a good approximation of the square root. I think that's probably been enough for today, so I would recommend spending some time getting familiar with arrays and how they interact with functions, as well as also take a look at some different recursive functions that you can try doing. Thank you very much for watching. I hope you have a wonderful day.